And finally, our last paper in this session is about a new sort of reverse problem in top K recommendations. So interesting to see this, and it's from Osaka University. Okay, fire away.
Hi. Can you hear me?
Yes.
Okay, good. Hi, everyone. I'm Daichi Amagata from Osaka University, Japan. I'd like to introduce reverse maximum in a product search. In this study, we assume a recommender system based on matrix factorization, MF. So we have a vector for each user and item. Actually, in the previous RecSys conference, MF shows a better performance than neural net-based recommender systems. This motivates our assumption. To make a recommendation list for a given user, MF considers the maximum inner product with the user. Given a user vector U and an item matrix P, we find item P star that has the maximum inner product with the user vector. This is called the problem of maximum inner product search, MIPS. This problem can be regarded as a user-driven service because queries are users. On the other hand, if you want to know users who may buy a given item, what we should do? This question appears in many applications which provide item-driven services, including effective advertisements and market size estimation. Now let's consider that a query is an item P. To answer the question, it is reasonable to find users whose MIPS result is P. Here, I formally define the problem of this study. First, K-MIPS problem. Given a set of vectors P, a query vector Q, and K, the K-MIPS problem finds K vectors in P that have the highest inner product with the query. Next, reverse K-MIPS problem. This is our focus. Given a query vector Q, K, and two sets of vectors, large Q and P, this problem finds all user vectors U in Q such that the query is included in the K-MIPS result of U among P and the query. To simply solve this problem, we can run a state-of-the-art K-MIPS algorithm for each user vector in Q. However, this approach incurs a huge computational cost. This is not feasible for large-scale recommender systems, so we should overcome this computationally challenging problem. I here summarize our contributions. We propose the reverse K-MIPS problem, and as its solution, we propose SIMFRA. This is a fast and exact algorithm. Actually, SIMFRA is easy to deploy if you use an MF-based recommender system. The code of SIMFRA is open source. We show that SIMFRA is theoretically faster than the straightforward approach. Also, our experimental results show that SIMFRA functions well on real datasets. For instance, for a dataset with 2 million users, SIMFRA needs only 0.5 seconds, while the straightforward approach took a half hour. Now let's go back to the straightforward solution. This approach runs K-MIPS algorithm for each user vector. This solution provides the exact result and can exploit existing techniques. However, it must check all user vectors, although most of them are not included in the reverse K-MIPS result. To avoid this drawback, we use two ideas. First, user vectors that are not included in the result should be ignored. Second, we don't need a K-MIPS result, and just yes/no answer is fine. Which means, given a user vector U, it is sufficient to know that the query is in or not in K-MIPS result of U. To implement these ideas, we make some data structures offline. This offline processing is done only once. First, we sort the vectors in non-increasing order of norm. Then by using order K-max vectors P, we make a low bound array for each user vector. Because we use only order k-max vectors, each element of the array is always not larger than the exact value of the corresponding rank. For instance, the first element of the array for U1 is lower bound of its maximum inner product. Last, we make blocks to group user vectors. For each block, we make a lower bound array that is an aggregation of lower bound arrays of the user vectors in this block. This preprocessing needs only order n log n time and on the n space, so it scales to large datasets. From these data structures, we have some merits. Now let me consider a user vector UI. If the inner product of UI and the query is not larger than the case lower bound of UI, we can say that UI is not in the answer. And this needs only a constant time. Yes case also has a similar result. If the inner product is not less than the product of their norms, we can say that UI is in the answer from Cauchy-Schwarz inequality. Besides, we have a case that we can say all vectors in a block are not in the answer in a constant time and in a batch. Now let's assume that UI is the first vector of this block. The product of its norm and the query norm is an upper bound of the inner product of the query and any vector in this block. So if this is not larger than case lower bound, all vectors in this block can be ignored. If UI does not have these cases, we use a linear scan P to know that the query is in the answer, in the k-MIPS result of UI. However, we can still always stop the linear scan whenever we can guarantee that the query is in or not in the k-MIPS result of UI. Our algorithm, simpler, incorporates the techniques in the previous slide. I don't talk about its detail, but the main result is its theoretical performance. Alpha is the pruning ratio of Q, a set of user vectors. And generally, alpha is larger than 0 in real datasets, so simpler is always faster than the straightforward approach. Also, simpler is actually easy to parallelize. Its efficiency can be improved by multithreading. Now let's see our empirical results. These figures show the impact of K. You can see that simpler is much faster than the baselines. And it is actually at least 5 times faster. Next, the impact of the number of users. And simpler scales well to larger datasets, and it outputs the result within 1 second. Next, the impact of the number of items. Simpler is almost not affected by this number because the linear scans are not done usually and the termination functions well. Last, the speed up ratio in case of multithreading. Although data distributions affect the performance of simpler, the running time becomes shorter with increasing the number of available threads. To conclude, we propose the reverse k-MIPS problem, and as its solution, we propose simpler. We theoretically show that simpler is faster than the k-MIPS-based solutions. Also, we empirically show that simpler is significantly faster than the baselines. That's all. Thank you for your kind listening.
Thank you very much. Any questions in the audience? No questions so far online. Can I ask you, first of all, a motivational question? I'm just wondering, you gave some good examples of where this problem might be relevant. I'm wondering if you came to this problem by some particular application. How did you come about to actually start to look at this problem?
Okay. And for instance, if a company makes a new item, maybe it wants to need to estimate the size of users who are interested in this item. Then this problem can be estimated. This problem can provide the estimation size of the number of users who are interested in the new item.
Okay. And did you have such a company who suggested this problem to you?
Actually, it's confidential.
Right. Okay.
But
okay, that's very good.
Actually, I am working with a Japanese company, and we are talking about it.
Okay. So you have some very impressive speed-ups against the state-of-the-art algorithms, but in some sense, the state-of-the-art algorithms were not directly trying to solve your reverse problem. So do you think there's more that can be done? Do you think that if more study is done on this problem, that you can get even more speed up?
I'm not sure. But actually the simpler is easy to price. So if someone use CPU-based parallelization, maybe more speed up can be obtained.
Right. And how about other identities? Like there are lots of identities to do with dot products and norms of vectors. Do you think there are some other mathematical identities that would help you to eliminate blocks of users from consideration?
Sorry?
So I'm asking you, do you think from the theoretical perspective that you could come up with better bounds than the ones that you're currently using in your algorithm?
Sorry, I can't hear that.
I'll try and phrase it another way. So your algorithm relies on asking yes/no questions about blocks of users to eliminate them. And what I'm asking is, do you think you can refine that step? Is there some way to come up with better bounds that would make that step more effective?
Okay. Actually, I'm not sure this is really tight upper bounds. So yeah, it's a very good comment and question. I'd like to more analyze its upper bound and lower bound.
Okay, we'll finish off with one. It's a comment online, so it's a very valid use case for marketing teams. If you have a set of items and you want to find SMS notifications for them, it would be good to find good combinations of items that give a reasonable sample size of users. So that's somebody online who's agreeing that this is indeed a very interesting problem to examine. Okay, we'll finish off and we'll close the session at this stage by thanking the speaker. Thank you very much. Okay, time for tea.